Today, we're diving into one of the most mind-bending, head-scratching mysteries our planet throws at us: ball lightning. Imagine this. You're in a thunderstorm, and suddenly, a glowing sphere, maybe the size of a golf ball or even a soccer ball, just floats through the air. It might be silent, lasting for seconds, perhaps even a minute, before either gently fading away or, sometimes, with a startling pop. Sounds like something out of a sci-fi movie, right? But these are real eyewitness accounts, thousands of them from across the globe. Ball lightning isn't your everyday static electricity. It's an atmospheric anomaly that has baffled scientists for centuries. The core puzzle? How does this seemingly high-energy ball maintain its shape, its stability, for so long without just dissolving into thin air? It's like trying to hold smoke in your hand, but this smoke glows and moves with a mind of its own. It truly defies our classic understanding of plasma physics. We've got incredible stories, like one from a 19th century French church where ball lightning reportedly entered, floated around, and then peacefully exited, leaving no trace, or even more dramatic accounts of it zipping through airplane cabins. So, what's going on here? Scientists have been scratching their heads, and we currently have two major competing theories, each with its own strengths and weaknesses. First up, we have the silicon nanoparticle hypothesis. This is a leading contender right now. The idea here is that when a regular lightning bolt strikes the ground, it superheats and vaporizes silica and other elements in the soil. This creates a fine aerosol of tiny silicon nanoparticles. The ball you see isn't traditional plasma, but rather these nanoparticles slowly burning or oxidizing in the air. This theory is fantastic at explaining why ball lightning can last so long. It's like a tiny, slow-burning firework. And it got a massive boost in 2014 when scientists in China actually observed natural ball lightning and, get this, its spectrum showed clear lines of silicon, iron, and calcium, exactly what you'd expect from vaporized soil. It was an incredible moment for this theory. However, this hypothesis doesn't explain everything. What about all those reports of ball lightning appearing inside aircraft or even emerging from power sockets, far away from any ground strike? If it needs a ground strike to create the nanoparticles, how does it pop up indoors? That's where the mystery deepens. Then we have the electromagnetic cavity model. This is an older, more theoretical idea, championed by Nobel laureate Piotr Kapitsa. This model suggests that the ball isn't a burning aerosol, but rather a self-contained plasma bubble. It's held together by its own super-intense internal electromagnetic field, almost like a tiny force field. Kapitsa even proposed that it might absorb energy from background atmospheric microwave radiation to sustain itself. This theory could potentially explain how ball lightning might pass through glass, as electromagnetic waves can do that. But there's a big catch. The amount of microwave power needed to sustain such a ball is astronomically high, levels we just don't typically measure in nature. So, while it sounds cool, the energy requirements are a huge hurdle. The biggest challenge in all this? We can't reliably recreate ball lightning in a lab. Imagine trying to study something that appears randomly, lasts for a few seconds, and then vanishes. The lack of a consistent, reproducible laboratory analog is incredibly frustrating for researchers. Adding to the confusion, reports often contradict each other. Sometimes it feels warm, sometimes it's cold. Sometimes it moves erratically, other times it's perfectly stable. It can interact with conductors or ignore them completely. This makes some scientists wonder if we're actually looking at several distinct phenomena that we've just lumped together under one name: ball lightning. Maybe some events are indeed burning nanoparticles while others are something else entirely. It is a bit like describing every bright light in the sky as a fuse and star, when some are planets, some are satellites, and some are actual stars. The more we learn, the more we realize how much we still don't know about our own atmosphere. Ball lightning is a fantastic reminder that even in our technologically advanced world, nature still holds countless secrets waiting to be unraveled. It encourages us to keep observing, keep questioning, and keep exploring the unknown. Who knows, maybe one day you'll be one of the lucky few to witness this incredible phenomenon, and perhaps even help us understand it better. What do you think about ball lightning? Have you ever heard any wild stories or perhaps even seen something similar? Let us know in the comments below. If you found this dive into atmospheric anomalies as fascinating as I did, please hit that like button, subscribe for more scientific mysteries, and don't forget to ring the notification bell so you don't miss our next adventure. Thanks for watching, and I'll catch you in the next one.